So this is chapter 10 for the AP review on chemical bonding, the second chapter of it. To begin with, this chapter talks about the geometry of molecules, referred to as the Vesper model, valence shell electron pair repulsion. What I'm going to do right now is go over an example of all these with you. Hopefully you will have a table that looks like this as well that goes over all the different shapes. If not, that's something that can supply to you. So if we look at all the different possibilities, the first bond shape is called linear. To draw a linear molecule, a good example would be carbon dioxide. Carbon double bond to oxygen. It's linear because it's bonded to two things, so there's no extra pairs of electrons on the central atom. There is, by the way, one unusual type of linear where you're bonded to two things with 3 pairs of electrons on it. Very unusual one, though. Bent would be the next one I'd talk about, and water is a good example of that. The reason why water is bent is its central atom bonded to 2 things, and there's electrons there as well. Either 1 pair or 2 pairs of electrons will bend the linear shape. Again, the 3 pairs is an unusual one for things that disobey the octet rule. So there's linear and bent. The next one is trigonal planar. Boron trichloride is a good example for that. Boron trichloride could also be, from the previous chapter, an example of something that disobeys the octet rule because it's an incomplete octet. Notice that boron only has 2, 4, 6 around it. What makes this trigonal planar for the shape is that it's bonded to 3 things, but there's no electrons on the central atom. So again, that's trigonal planar. The next one can be trigonal pyramidal. Trigonal pyramidal is still bonded to 3 things, but it has a pair of electrons on the central atom. So unlike the boron trichloride, it's going to shift everything down a little bit. So again, I'm just going in order on what I have here, so you can have an example as you go along there too. So here is your ammonia example for trigonal pyramidal. T-shaped is the last version that we have when something's bonded to 3 atoms. In T-shape, you have a central atom that's bonded to 3 things, and there's 2 pairs of electrons on the central atom. If we move on to things bonded to 4, tetrahedral is the first example of that. Tetrahedral is bonded to 4 atoms for the central atom with no extra electrons on it. The next version would be called seesaw or distorted tetrahedron, where my sulfur is going to be bonded to 4 atoms. With a pair of electrons on the central atom. So what makes this one again different is because it has a pair of electrons on the central atom, it will distort that original tetrahedral. Square planar is the last option. And in square planar, once again bonded to 4 things, but notice there's 2 pairs of electrons on the central atom. That 2 pairs of electrons is once again going to make the 4 bond things be in a flat plane. Above and below are your electrons that are going to cause that to stay in what's referred to as the equatorial position. A couple more left on this sheet would be things that are bonded either 5 times or 6 times. The first being trigonal bipyramidal. Phosphorus pentachloride would be an example for that. This is something else that I might have brought up in the last chapter with things that disobey the octet rule, because now it's going beyond 8 outer electrons. 2, 4, 6, 8, 10. So phosphorus pentachloride is going to be what's called trigonal bipyramidal. The last 2 are square pyramidal, which bromine would be bonded to 5 fluorines in this case. And it has 2 electrons on its central atom. Nice work, everybody, by not applying to that too much. So, again, 5 things with 2 electrons on it is going to be called square pyramidal. The very last version is going to be called octahedral. Octahedral is bonded to 6 things like sulfur hexafluoride. And I can fill my electrons around all the sulfur then to show that it's bonded to 6 things being octahedral. This is one of the things that you just have to memorize though. You have to know all these shapes, so either draw out the molecule and give the shape, or here's a molecule, just tell me what the shape is. So we move on from shape. The next slide is going to be talking about dipole moment. Dipole moment talks about indication of electron density. So this determines the polarity of a bond or a molecule. The example I'm going to give you on the board is carbon dioxide. So this is a lot less drawing than what we just had to do. So once again, here's carbon dioxide. Dipole moment, what I look at is the electronegativity of oxygen and carbon. They are not very similar. Again, more than one step away means you are going to be a dipole. The dipole is an arrow showing the direction of electron density. The electrons are going away from the carbon more towards the oxygen in that unequal sharing, which means this bond right here is a polar bond. Again, a polar bond is an unequal sharing of electrons. The problem with carbon dioxide is you have a dipole going in the opposite direction as well. Typically, a polar molecule has a positive end and a negative end, but right now, carbon dioxide has two negative ends. So even though it has a dipole, carbon to oxygen, overall the dipoles cancel each other out, and it's going to be a non-polar molecule instead. The next thing the chapter goes over is the different hybrid orbitals. So here are the possibilities. You can be sp3 hybridized, sp2 hybridized, sp hybridized, sp3d, sp3 and d2. So what I'm going to do is draw an example of each of these, and it's something where I'm not certain you need to know how they work as much as identification. Draw a molecule, tell me what it is. So in this case, sp3, what I would do is count 1 s and 3 p's. Something that has 4 bond points coming off of it would be sp3. A good example of that could be methane that I drew earlier, CH4. So it has 4 bonding points. That would be called sp3. Something that sometimes confuses students is not only do bonds contribute to that, if I gave you the water example again, water is technically sp3 hybridized. Yes, there's only 2 bonds, but there's 1, 2, 3, 4 bonding points within the molecule. 2 of them are lone pairs, 2 of them are bonded pairs. So water is a second example of sp3. So keep that in mind. That's not just bonds that determine hybridization, it's bonds with electrons on that central atom as well. sp2 would mean there's only 3 things coming off of it. The boron trichloride we did before is a good example of that. So here is sp2. Again, you can fill electrons around the chlorine if you'd like, but there's only 3 spots, S, P1, P2, so again, you're looking for 3 things there. Sp would be even less than that, it would be 2. An example of sp hybridized could be acetylene. Acetylene is C2H2. There's a triple bond between each carbon. You'll notice that each carbon is only bonded to 2 things. Sp is only 2 things. So if you count the letters, it tells you how many times things should bond. In this case, again, only 2 times for sp hybridized. The last 2 of them, sp3d and sp3d2, you'll notice include the letter D. These are the ones that disobey the octet rule. They disobey the octet rule because they have access to the d orbital. sp3d has 5 total letters, 1 s, 3 p's, and a d, which means it should make 5 bonds. The phosphorus pentachloride example that I gave you when we talked about shape is a good example of sp3d, because once again there's 1, 2, 3, 4, 5 bonding points. So that's where the 5 comes from. Again, this does disobey the octet rule, but it's okay because it has a d orbital to put extra electrons in. Lastly, sp3d2, if you count the letters there are 6 letters. Sulfur hexafluoride, which was the last example I gave you on shape for octahedral, is a good example for that. In sulfur hexafluoride, again, 1, 2, 3, 4, 5, 6 bonds, that's where the sp3d2 comes from. It does disobey the octet rule, but it can by putting electrons in the d orbital. So this is another thing, just like shape, where you should be able to draw out the molecule and then tell me what is it. Is it this shape? Is this hybridization? Something to that effect. second to last slide that we have to go over is what sigma and pi bonds are. A sigma bond involves orbitals overlapping end to end. So again, when two nuclei are coming together, their electrons will overlap in the middle. That's a sigma bond. A pi bond is what's referred to as a sideways overlapping, because once one bond overlaps in the middle, the rest have to go above or below, front, back, something of that nature. So formaldehyde is an example I can give you for that one. Formaldehyde has this structure right here, which if we want to review shape right now, 1, 2, 3 would make a trigonal planar. If we want to review hybridization, it's sp2 because there's 3 spots to it. Now what's happening here is any single bond is going to be a sigma bond. So this is a sigma bond. This is a sigma bond. The first bond between carbon and oxygen is also a sigma bond. So I would say that there's 3 sigma bonds in this picture. Once you deal with double or triple bonds, that's when pi bonds start to come about. So this one right here is going to be the 1 pi bond that we have. And again, just like with shape, just like with hybridization, I believe the thing that you have to know is, here's the molecule, tell me how many of each there is. So there are 3 sigma, there is 1 pi in this version. The very last thing to mention is what's referred to as molecular orbital theory. This results from the interaction of atomic orbitals of the bonding atoms and are associated with the entire molecule. So too often what we do in Lewis dot and things of that nature is we show that here's an electron from one atom, here's an electron from the other atom, and it only has to stay with that. Keep in mind that there are a lot of different bonding theories out there. One of which says that the molecule shares all the electrons within the entire thing. So it's not designated as a carbon electron in this picture, or a hydrogen or an oxygen. There are electrons for the shared group instead. That is the last part of this chapter, the second chapter on bonding.